Today, we will do something very exciting. We will control our robots without the joystick. What we will cover today will somewhat related to T3 and T4 as well. In the midterm, you guys can use the joystick to do something exciting. And now we would like to add some AI to your DocuBot so you can do it without the joystick. Okay, so for example, maybe we can do something about following or chasing, or some obstacle avoidance, or some navigation. Okay, so we will cover some theoretical part first, but not too much. Just try to cover the minimum of the theory so that you know what we are doing and we have the same terminology. In the second part, we have Yuri here. The nice thing is that he can do something very, very cool already, control the DocuBot from a phone, either by a Bluetooth or a Wi-Fi. So some like engineering work has been done already. Okay, and next, Brian will talk about send card commands from Jupyter Notebook. Okay, that could be, I think that's a very nice material to, to import even ROS package inside Jupyter Notebook. And you can do something, for example, to turn, to go straight, or turn right, turn left, etc. Okay, and the last part, again, I wish you can play with the starter code and develop the code for your own project. We will take some materials from some textbooks, but just the minimum amounts that we will cover for today. So the first one is the mobile robotics. So this book is written by a professor in CMU. And the other one, planning algorithm. This is more like a classic planning algorithm book. And the other professor is in UIUC. We will start with the motion primitives for today, and we will also talk about solving problem by searching. And for the second part, that's about the AI part. And I think in the second lecture, we already talked about A-star search to do some path planning. First of all, what's a motion primitive? And so let's take a short definition here. It's a motion primitives. It's a finite number of state and control trajectories. Okay, and then you can combine them to generate some other trajectories. So if we take a look at the bottom left, you can see that suppose your car is right here, okay, and you can do something. For example, you can just go forward, or bear left, bear right, or right. Okay, that's kind of straightforward, right? And if we take a look at the bottom right, and we can see a triangle and obstacle over there. For example, if you take this path, you can have the 5 motion primitive again. But in this situation, you will be able to move just forward, bear left, and left only, right? Because the bear right and right primitives are not feasible for this obstacle, okay? And this is another example. If you go forward, you can get another 3 nodes over here. But if you go this direction, you can expand all 5 motion primitives again. In short, depending on the configuration space, so we usually also call it a C space. So the C space usually have a few obstacles, and you can grow your tree. It's more like a tree, and essentially it's a graph from the starting point to somewhere. Okay, and based on those motion primitive, you can grow this graph somehow without and try to avoid the obstacle and reach the goal point. It's the more formal definition for the motion primitive. So essentially, it's in short, it's within a time interval. Okay, and you have a finite number of state. State here is the X. Okay, and the control is the U. Okay, so for example, if in our DocuBot, the state at 2D, that could be maybe just the location X, Y, and the heading of the DocuBot. Okay, and for the control, it could be just the straight, the velocity, or maybe the angular velocity, either turn left or turn right. There is a figure down there, and this is about more like a state transition diagram for a flight or for a hawk flying in the sky. Okay, so you can see the hawk can just do the forward flight, and it can steady turn left, turn right, or just hover on the sky. Okay. And actually for this part, we can also ask our DocuBot to do something similar, but not necessarily. And next week, we will talk more about the state. Okay, so we will have something like this, a finite state machine. And for example, if you are in the land following state, and you can switch to others, okay, and do some different behaviors. Okay, and you may be curious that where does the motion primitive come from? Okay, and actually, if we use something very, very simple, for example, this is one of the basic Dubin's car, and it's a more like classical toy example ever in the planning algorithm. And it can just do a straight, left, and right. Okay, and straight, that could be just straightforward, right? You just have some velocity forward, and you have no angular velocity, and you will just go forward, right? And that could be pre-computed. So essentially, within a time interval, you change the control command somehow, and your state X, Y, and the heading will change accordingly. Okay, and it could be also pre-recorded. There is an analogy for Kung Fu script. For example, if you are playing a video game, and you know that some Kung Fu movie, they can capture the motion from a motion capturing system, and it can be a kick or a punch, right? And you can try to combine some of those motions and become some kind of fist, right? It's like a Kung Fu movie, okay? And so, yes, so for some more complicated motion, it could be pre-recorded. So for example, it could be some kind of curve, right? And it may be difficult to use the equation to show this kind of a curve, okay? But in most of the case, we can just use some, for example, the curve, maybe for example this one to the left, and it could be just you apply constant straight velocity, and you also apply some angular velocity, right? And you will do some like use sine or cosine to represent those primitive. Okay, so the second easiest typical example is the reed shape car, and that's just the forward and backward version of the Dubin's car. Okay, so now we have those motion primitives, and we would like to use them to do something a little bit more interesting. If we can have a sequence and have those primitives in our sequence, that could be something very interesting. So for example, on the bottom left, we started from here, okay, and the heading is up. And you can see that the Dubin's car can do a turn right with alpha angle, right? Alpha degrees. So the heading will become like the X, Y, and the heading will become X, Y is here, and the heading is pointing this direction. And we apply go straight for D, right? And we will reach this point. And now let's apply left for gamma degrees. Then we can reach this point. You can do exactly the same thing. You start from here and you turn right for alpha, and you turn left for beta, and then turn right again, gamma. So you will essentially walk from here and have a curve and reach this point. Okay, so far so good. And you can see that the RSL for the bottom left, or RLR for the bottom right, that could be something like a language. The good thing is that we can also apply something similar to do something cool in our DuckyBot. Here is an example. So the scenario is that we found that the DuckyBot A is broken on the road, and the second DuckyBot want to maybe just pass the DuckyBot 8. Okay, so maybe we can just do something simple. Okay, and this is the Jupyter Notebook. Okay, and hit enter. Okay, so yeah, so this is probably something very similar to what Little Car want to do, right? So Little Car also try to back off a little bit and try to tow this broken DuckyBot away, right? Okay, so this is one of the example. And one thing different from, between Dubin's car and DuckyBot is that the DuckyBot can actually turn without moving, right, at the same point. So that could make the problem a little bit easier. That's okay, we can just start from something easy. Maybe the second example. So again, the Jupyter Notebook. Okay. Okay, so actually the DuckyBot is moving even without watching, right? The camera is actually at the front. Do you remember that when you try to do the backward, reverse, or parallel parking, how did your coach teach you? Maybe do you see maybe there is a marker somewhere, and then you turn maybe 2圈半, and then and then come back, and then you see another marker and put it back. Okay, then yeah, you're good. So now you have maybe some object detector or some different detector, and you can do something similar, 2圈半, right? And then you can do something very similar for your DuckyBot. That's about some very, very brief introduction for motion primitive. Next, let's talk about some artificial intelligence and some problem solving by searching. Okay, and this is it's a typical AI textbook. This is a very, very popular one. And for myself, I used this maybe like 10 years ago, and then it was second edition, and now it's the third edition. Something different, like 10 years ago, I think we have some Java code along with this textbook. And now you have Jupyter Notebook and Python with this textbook. And the examples become very clear and great visualization, much better than what we had 10 years ago. Yeah, I'm very glad to see that. So this book keep improving over time. Maybe the big O notation, complexity. Okay. And yeah, that's also some important topics in AI, but we won't tell too much about it for the lecture today. So we will a little bit focus on the search, and we will also discuss what's the difference between different algorithms. This is an old slide from our second lecture. Previously, that's the very short demo for path planning algorithm. So giving a map, configuration space, starting point and goal point, and a heuristic function. And you can use different algorithms to reach the goal. Okay, so yeah, so today we will talk about the A-star. And this is the old video. Just I will just play this some of them to refresh your memory. Okay, so you can see maybe the orange part. That's probably you have different way to generate those the graph. Okay, and maybe some of them are feasible and some of them are not. Okay, so this is what we want to talk about for today, and this is an example in the AI textbook, and the goal is to reach full chart rest from a rate. You can see that there are a few cities in this map, and you can also see the cost, maybe the travel, the actual distance from city A to city B. So now suppose our starting is from here, and we want to reach this point. How would you like to plan your trip? Maybe you want to find something, the optimal one, the shortest one, right? Maybe from here to here, and maybe to here and here. So you just need to travel to 1, 2, 3, and 4, and you are there. Okay, but maybe this one we just you use your instinct to do it. But for AI, we need to formulate the problem a little bit. Okay, and one way to do it is to build a tree for it. So we start from here, and then if we go back, and you can see that from the starting point choices, right, 1, 2, and 3. So that's what we are talking about. We have 3 options to go from here to here, or to here, or to here. Okay, and for each one, each city can reach to the next one, right? And you may find some bug there, like you may go back to the same one in a loop. Years ago, when I took this course, we also need to do some coding to check that we are not go back to the repeated city. Okay, so suppose we have done that, and in that case, we can build a tree like this. Okay, and we go from this city, and we have 4 other options, and so on. Let's start with the breadth first search. Suppose you have an A, okay, and the algorithm, we can actually, there is a formal algorithm section in the textbook, but we will just explain the idea by example. So we start from A, and the breadth first search named after what it is doing. So we can expect that the second node will be here. So we try to expand to B and C, and we will go through each one. So we have A, B, and then C, okay? And let's try to explain the childs again. So we have D and E. Okay, D, E, and then F and G, and etc. Okay, so this is kind of straightforward. You just finish finding every single node at the second level, and then you dig deeper, right? I want to show you something. So this is the first algorithm. We need to think about the cost for time or memory. Okay, so you can see that the depth is from 0. You can see there is only one node. And the computation time could be very, very short. It could be just 1 millisecond. And the memory could be small. It could be just 100 bytes. But if you can see that when the tree, depending on how many sibling nodes, you will have more nodes, and you will spend more time and more memory to store everything and to compute everything. You can see that when we go from 0 to 14, you can see the node expand very quickly, exponentially. Okay, and the computation time also grow very fast. So you can see that at the depth at 14, we will have to spend 3,500 years to complete your project. So your advisor is not going to allow that, right? So even that maybe 10 years later, your computation is 100 times faster, and you will still need 35 years, right? And you won't be able to graduate by, by this algorithm. Okay, and you can see that also the memory. So now probably if you have a game, if you have a very nice desktop to play a game, and you may have 12 gigabyte GPU, right? But, well, this is still too big to hold everything in your memory. Right? So even like 10 years later or 20 years later, you won't be able to solve a problem by breadth-first search. Okay, so the second algorithm is called depth-first search. So we just explain the deepest unexpanded node. So we start from A and we expand it to B. And by its name, we are going to go deeper, right? So D and M. So which one is the next? E, okay. N, maybe J and then K, right? And what's next? C, and F, and maybe G? No? L? Okay, and M, and go back to G, and then N and O, right? Okay, so you got the idea. That's the depth-first search. So let's try to see if you can graduate by this algorithm. Okay, so the good thing is that the memory is very efficient in this case. If you want to find a solution, you just need to go to the deepest node, and you can forget everything else. The other thing is about the time. The good news is that we have a chance to find the solution very quickly without exploring all the nodes, all the search space compared to breadth-first search. And the bad news is that you may get stuck going down to a wrong branch. And then if the branch is very deep, you won't be able to get not even a chance to get an even okay solution. right? So depending on your problem, and if you have a very large and very deep search tree, that first search, well, may or may not be your good choice, maybe not. So far, we just try to explore the whole graph in different ways, right? Without using any information. We just just try everything, try to explain breadth first search, try to explain all the nodes. And that first, we'll try to go deeper no matter what, right? Without having any information. This is why we want to use some of because in the real world scenario, we always have some information to use. Okay, so on the map, for example, from the starting point to the next city, we actually have a cost from city A to city B. We also have a table over here. This table is actually, so suppose we have the GPS location. And the GPS location for each city will tell us what? For example, the straight line of distance to our goal, right? And because for each city, we assume that we have probably the GPS location, and we can see this. So this is our starting point, and that's 366. And yeah, this is the goal point, so that's 0 for sure. And you can find that the value, the straight line distance is always shorter than the actual one, right? Because you can imagine that the road could be curved or somehow and take longer. We have those two informations. Okay, then let's see how can use them. First search we would like to use is called greedy search. And we use a function, a heuristic function, but the function is only take advantage of the straight line distance. The algorithm will evaluate, okay, now suppose I have 3 options. I will see, okay, number 1, how far away this city straight line distance from A to the goal, and B and C, etc. That's the only information the greedy search want to use. Okay, and let's try to do that again. Okay, we start from here. This is the starting point, and according to the table, the straight line distance, the table on the right, we can see the distance is 366. Next, we try to expand the nodes, and we can see this is option number 1, number 2, and number 3. So the first one, that's 253 kilometers to go, and the second one, 300 something, and the third one, 374. So according to our greedy search, we definitely want to get this one, right? Okay, so let's expand this node, and we have 4 child nodes here. And again, according to the straight line distance, we want to pick this one. And next, bingo, we are there. So it seems that it's not too bad, right? It's kind of good. We just have 4, 1, 2, 3, 4, and done. Okay, here is the question. So is this the optimal? Optimal means the cost is the smallest, right? According to the greedy search, we just go from here, we expand the nodes 1, 2, 3, and we pick this one, right? And now we have 2 more options and expand, and we are here, and finally we got to the goal over here. Okay, so is this the optimal solution here? Can you find somewhere else that will actually the total cost will be lower. 好，所以我们如果说走，你说走这边吗 ？OK， 然后这里，然后在这边 ，OK， 对。那其實如果說你們可以有很強的心算能力的話，你們應該可以發現說，走下面事實上它的 total cost 會比較低。So the greedy search is kind of similar to depth first search. It will usually follow a single path all the way down. Okay, but we need to be careful of dealing with the repeated state. So otherwise, it will stuck somewhere. If you there are some situations that you may go to a dead end. And you will never go out. But usually, although the greedy search, it won't always give you the optimal solution. It usually gives you a good solution. So greedy search is sometimes still very useful if you are not very picky about getting a very good solution. Okay, but we have a better way to do it. Okay, so let's take a look at the A-star search. And the idea is that try to avoid expanding paths that are already expensive. So the difference is the evaluation, the heuristic function. And you can see that our f of n is equal to g of n and h of n. And this one is exactly the same, right? And this one is something different from the greedy search. Let's do that again. So we have again, we start from the starting point, but you can see that the evaluation is a little bit different from previous algorithm. And we have the 0 plus 3, 68, and 0 is the cost so far, okay? And right, and let's see, this is 140 plus 253, and previously we don't really take the 140 into account. Okay, here, that's the kind of the branch there. On the second pass, that could be a optimal one, right? So over here, we can evaluate. We have 4 options here, and we can actually calculate the cost differently from the greedy search. And we want to pick this one first, because that's 413. But this one is actually pretty close, right? 415. But okay, let's expand this one first. When we expand the node, you can see that those 3, because we also consider both straight line distance and the cost you already spent. So you can see that the total cost over here, 500 something, 417, and 500 something. This one is actually not the smallest in our old situation, right? So we will go back to this node and expand the node. You will see something strange that when you expand this node, you already see the gold, but the A-star search is not going to go to the gold directly. It still try to evaluate what would be the possible way to reach it, okay? And so let's pick a 417, this one, and expand the node. And okay, so from this node, we can actually get to the gold with less cost, right? Okay, so you can see this is 418, right? and this is a 450. If we do a comparison between greedy and A-star search, some property you will want to know is that is it complete or optimal? The complete means that you will always find a solution. Okay, the optimal means that you will find the best solution. For A-star, the good thing is that yes, A-star can be complete and optimal. And there are also some proofs in the textbook. And the time is also efficient. But the only downside for A-star is that the number of nodes is exponentially to the length of the solution. Okay, so right. So that's because in our previous example, it will not throw away previous nodes. It will keep evaluate all the node you expand, right?